Namaste, welcome. We will take a complete look at the issue of singular value decomposition. We have reached some distance. More importantly, we know the following now. Suppose we have matrix A which is say M cross M, which is real symmetric, then we do eigenvalue eigenvector decomposition of this as A xi is lambda I xi, let us say I equal to 1 to n. We can even assume lambda I to be distinct, in which case we can get a matrix M. By definition, this matrix is the eigenvectors corresponding to distant eigenvalue. This has a property that M inverse A M will be diagonal matrix. In this case, since it is orthogonal, that is this set of eigenvectors corresponding to distant eigenvalue for real symmetric matrices is orthogonal, we can even make it orthonormal, in which case M transpose A M is D. This is the result on orthogonally diagonalizable. What? A is a real symmetric matrix with distinct eigenvalues. Note, even if the eigenvalues are not distinct, you can still find it by a process like Gram-Schmidt orthonormalization process, which is basically projection, application of projection. So, what are we interested in? We are interested in the following. We want a matrix A M cross n to be found equivalent to a diagonal form. That is the question, because if A can be found in its diagonal form, when I say diagonal form under quotes, we are also looking at the problem, associated problem of actually inverting a M cross n matrix. So, these two are related, we will see that they are actually related. For example, if you had square matrix A x equal to B M cross M, X was A inverse B, assuming that it is non-singular, all that. So, I basically want to again look at solving the problem A x equal to B M cross n with M not equal to n by some idea of A inverse for this, which is equivalent to A inverse B equal to X. Of course, we saw this generalized inverse to be equivalent of that to be A transpose A inverse A transpose. And we also saw that we actually end up solving A cap B cap equal to x cap, and we actually solve for x cap and not equal to x. Okay. So, again this diagonalizability here was related to A square matrix, was related to the eigen decomposition lambda I xi. So, we want some eigen decomposition, eigen like decomposition. Of a matrix A which is m cross n with m not equal to n. That is the first step. First step we solve. Step 1 of solving, making A which is m cross n into a square matrix. There are two square matrices associated with this A transpose. These are both square and real symmetric whenever A which is m cross n is real. This is, so somehow we have found a close cousin of A which is m cross n to be two equally cousins of A transpose A and A transpose, and as you can guess A transpose will be m cross m, this will be n cross n, different size. So, this is first part. Second part is we wanted eigen decomposition. Suppose I look at I lambda minus A transpose A or other one I transpose minus A transpose. Of course, this size A transpose A will be n cross n, this will be m cross m. Okay. So, in principle I can do the eigen decomposition of that. So, what do I get if I do? Just recall two factors. If lambda is an eigenvalue of A, lambda is also an eigenvalue of A transpose. 1. Second part is, if lambda is an eigenvalue of A or A transpose, then lambda squared is an eigenvalue of A squared or A transpose A. In this case I am looking at A to be square. These are for square matrices. So, conceptually we are doing the following. We have a matrix A which is m cross n with m not equal to n, and I have found I can even assume m to be greater than n. So, I can do two things, A transpose which will be size m cross m, or I can have A transpose A which is n cross n. Whatever we do we get the same result. It is always better to work with a smaller size. We also know something, the rank of A which is m cross n is always less than or equal to minimum of m comma n. Okay. So, if minimum of m comma n, in this case it will be n. So, this rank of A cannot be greater than n, at most n. So, what we do is we define singular value as square root of lambda I squared. where lambda I is an eigenvalue of A transpose A, which anyways will have eigenvalues being square. This will. So, you do the eigen decomposition of I lambda minus A transpose A. What eigenvalues you get? You will get typically lambda 1 squared, lambda 2 squared, etc., lambda n squared at most. The original matrix, suppose you had a square matrix A m cross m, you had eigenvalues lambda 1, you had another eigenvalue minus lambda 2, let us say, but suppose I took A transpose A and did the eigen decomposition, I will get lambda 1 squared and lambda 2 squared. So, the positive sign only remains as it is squared. So, we define singular value very similarly, we define singular value as sigma I is square root of lambda I squared. So, this will always be positive. So, this is one problem with singular values. Suppose the original matrix had a negative eigenvalue, it does not get reflected in the singular values. Barring this, all other phenomena associated with eigenvalue eigenvector is preserved. So, these are called the singular values, and we will see how this is getting structured in the diagonalization, consequently the inverse of a non-square matrix. Recall, if you had a square matrix A m cross m and you were able to diagonalize, this is equivalent to diagonal matrix which has entries lambda 1, lambda n. These are all zeros. Of course, you took a unitary transform M made up of eigenvectors and M transpose M was identity. Here A is M cross n with M greater than n. So, it looks like this. So, this is first row, second, all the way m rows. This is the first column, second column, all the way n column. Please know n is less than m. So, this is m, somewhere here is n. So, the diagonal equivalent of this will look like this, sigma 1, sigma 2 all the way to sigma n, rest of it 0. And if in the case when m is less than n, it is a fat matrix and it will look like this. This will have sigma 1, sigma 2 all the way sigma m, and this will be 0. So, this is the diagonal equivalent of a non-square matrix m cross n. This is the case A with m less than n, this is the case where A where m is greater than n. So, how do I get this structure? How do I get this structure? Again we recall. What do we recall? If A is real symmetric, there exists a m such that m transpose A m was D. You did not have much problem here because A was M cross M, this was M cross M, this was M cross M, this was M cross M, which means A gets operated by a unitary transform from the left, A gets operated by a unitary transform from the right, that results in diagonalization. A is basically factored out, A is stretched out, pulled apart, and D part sticks out. Okay. So, similarly here A I need M cross N. So, what does A do? A takes all Rn vectors to Rm vectors, correct. This is what A does. Whereas here A took all Rm to Rm, there is no problem with this. So, here similarly I need the following. I need something from the left to operate on A, which is M cross N. I want something on the right to operate on A, but the left one has to be M cross M, the right one has to be N cross N. The right one is N cross N. The N cross N sits here, the M cross M sits here. So, further I need the following. What do I need? When I had A, which was real symmetric, I did M transpose AM was given me diagonal form. This M was orthonormal matrices, orthonormal matrix made up of eigenvalue eigenvectors of A. Very similarly, I need the following. I need something on the left of A, which is M cross N, something on the right. This right one is N cross N, this is M cross M, this belongs to Rm, this belongs to Rn. So, I do the following. I take A transpose A, which is now a N cross N matrix. I do the eigen decomposition, I lambda minus A transpose A. Let me say the eigenvalues now are lambda 1 squared, lambda 2 squared, etc., lambda n squared. I call these square and I take the square root. So, the singular value sigma I equal to 1 to n now, are sigma 1, sigma 2, etc., sigma n. We can do ordering such that sigma 1 is greater than sigma 2 is greater than sigma 3, etc., etc., greater than sigma n, greater than or equal to ordering. Correspondingly, we will have not eigenvectors, but what are called singular vectors, which has many interesting things. What are these singular vectors? What are these singular vectors? Recall what are eigenvectors. If A was M cross M and it had eigenvalue eigen decomposition as A xi is equal to lambda I xi. A is m cross m. The eigenvector sets these vectors belonging to Rm. Of course, lambdas are belonging to the field. So, what did A do on xi, that is when you operate A on xi, what does it do? This is in the Rm space. A by definition operates on xi. Suppose I have some vector xi, let us say this xi. I operate A on that, action of A on that. What did A xi do? It ended up simply taking xi and scaling it by lambda I. So, if this was eigenvector, depending on lambda is either stretched, or in other case if the eigenvalue was negative, it would. So, basically any action, for example A of A xi is A squared xi, which is lambda squared xi. So, any number of times you A to the power n xi simply does the following: it takes the eigenvector which belongs to Rm and does the following. It simply scales positive or negative by lambda, lambda I squared, lambda I cube, whatever you do, the original eigenvector simply scaled along that, it does not change direction. So, it is invariant under action of A. The space spanned by these eigenvectors are called one type of invariant subspace, invariant to action of A. This is fine. Now, what do singular vectors do? What do singular vectors do? They must do something similar, but with small change which is obvious, but nevertheless has to be explicitly shown. So, now we have A which is m cross n, which means what does A do? A takes all Rn vectors to Rm vectors. Let us say these vectors are x1, xn. What does Axi is basically something that belongs to Rm, whereas xi belongs to Rn. So, the action of A takes vectors in Rn to Rm, you are here. Suppose you have a singular vector A transpose A xi, we will even define the, will be sigma I yi. So, if it is a singular vector, the action of A xi, right, this is m cross n, x belongs to n cross n, this is from the eigen decomposition, will be sigma I yi. So, some other singular vector yi in Rm space gets scaled by sigma I. So, similar to eigenvalue eigenvector pair, which is A xi is equal to lambda I xi, you now have AXI equal to sigma I yi, where xi belongs to Rn, yi belongs to Rm, sigma is singular value. This is what is happening. So, the action of A on the singular vectors, which was in the real eigenvalue eigenvector space here, simply was stretching. Now, the invariance is in the other space. Okay. So, since n is less than m, in principle it is possible to find x1 all the way to xn, correspondingly sigma 1 to sigma n, such that AXI is sigma I yi I equal to 1 to n, where these xi's come from eigen decomposition of A transpose A, which is now a n cross n matrix. So, you still do the classical eigenvalue eigenvector problem, classical eigen decomposition problem, but on a cousin matrix which is now real symmetric, by definition is A transpose A or even A transpose. You can do that. Only thing you will have to do on a much bigger size, you will have more 0 terms, but nevertheless the result is the same. Okay. And the invariant vectors, invariant singular vectors are in the transformed space. Invariant singular vectors are in the transformed space. That is, the action of A acting on AXI will give me sigma I yi. So, the final structure, and please remember this is purely geometric. We are not talking of formula here, we are talking of singular vectors and singular values. So, the final structure, how do we build? Again we recall unitary matrices of the type. If M is unitary, M transpose M is identity, which is same as MM transpose. This is square, let us say M cross M size. What was the diagonalization problem? Diagonalization problem, you would have matrix A real symmetric. So, you diagonalize it by finding M transpose AM is equal to identity, or even M A M transpose, that will also give you identity, with the property that MM transpose equal to M transpose M is identity, which are unitary matrices. So, for A, which was M cross N, you wanted a left operator which was unitary, I mean M cross M. You had a right operator which was simply the transpose of that. If this was M, M transpose did the job, it was also unitary. All come from the same space Rm. For SVD, Your problem was you have A which is m cross n with m not equal to n. So, I want a very similar decomposition of A where I have a diagonal form, let us say sigma 1 to sigma n, the rest of it is 0. This will be size m cross n. I need something on the left which is some matrix which I will call U, which is m cross m. On the right, this belongs to Rm. V, which is n cross n, and the vectors here belongs to Rn, such that U transpose is I m, V transpose is I n. And this will result in diagonalizing a m cross n as U. This is termed sigma, the structure V transpose. Very similar to if A was m cross n, m cross m, I would have had m A, sorry, m d. M d m transpose, which is same as m transpose A m equal to d. So, very similar to that is what this is. So, the working is like this, working of this. From A, which is m cross n with m not equal to n, construct the eigen decomposition I lambda n cross n minus A transpose A. So, eigen decomposition, call that V I, right, equal to 0. This is n cross n. So, I now get a set V 1 to V n, which is orthonormal. I will define that V to be this V 1 V n. So, this is A, this is on the right. The right is m cross m, R m, this is R n. So, I find a V matrix of orthonormal vectors, eigenvectors or singular vectors in this case, left orthonormal eigenvectors, left orthonormal singular vectors of A. This is the matrix V. How do I find U? U is m cross m. So, I do A V I equal to sigma I U I. This is U. So, assuming convenience, which is not necessarily best, but even if it is not so, it can be worked out. I am going to get U1, U2, Un, right, which are singularly transformed vector eigenvectors of AVI, right. This can be orthonormalized. This is orthogonal, it can be orthonormalized. So, I have partly the U, part of the U. What do I do to get from Un plus 1 all the way to Um? These m minus n vectors, where are they? they do not belong to V, because V only has 1 to n. This is similar to what is done as a basis extension problem. What is basis extension? Now you have a basis u1 to um, extend it to um plus 1 all the way to un. This comes from the null space of V, or you can construct it right here. Okay. So, basically you can do a orthonormal extension of set u1 to um all the way to um plus 1 to un. So, now you have u, which is u1 all the way to un, which came from AVI sigma I ui. This, because this dimension is m, which is greater than n, you can find m minus n non-zero vectors which give you, which are linearly independent of the set u1 to um. That is all that is needed. So, now A is u sigma V transpose or u transpose A V is sigma. This is the singular value decomposition of A. Of course, if A is m cross n with m less than n, this sigma will look like this. Connections. These singular values and the corresponding singular vectors A Vi is equal to sigma I ui. The singular vectors here, right, ui to ui to un is equivalent to the principal components of a real symmetric matrix. That is, whenever you had A m cross m and real symmetric with distinct eigenvalues, real symmetric matrices, you had eigen decomposition lambda I xi, A xi is lambda xi, and these eigenvectors give you what is called the principal component. The first eigenvector is the first principal component, the second eigenvector is the second principal component, etc. Whereas here this is far better captured, and in fact in the data space the singular vectors look like this. This is sigma 1, the next one is orthogonal to that, which is sigma 2, that is the length of this. So, in 2D the sigma 1 sigma 2 generate a ellipsoid ellipse data. Suppose you have another eigen singular vector sigma 3, it will be ellipsoid with sigma 1 sigma 2 as a, this will be as a major axis and minor axis. This will be ellipsoid. In general, you will have a n dimensional ellipsoid. and you had an interesting result that sigma 1 was greater than or equal to sigma 2, is greater than or equal to sigma 3, etc., greater than or equal to sigma n, greater than 0, greater than or equal to 0. So, this is in some sense the entire beauty of singular value decomposition, where the decomposition can be done only by doing corresponding singular decomposition of space Rn Rm. So, simultaneously you have to work on both spaces, and you basically look at the invariant singular vectors and then collect that set. You do an algebraic extension or even geometric extension if you want, generate the entire set for this. So, you have both AUI giving you eigen decomposition, singular decomposition. Now, suppose you had A which was m cross n and you ended up doing, and we know m is greater than n, suppose you ended up doing A transpose which was m cross m, you can still do that, you will get the same result. The only problem there will be you will have V1 to Vn, in that you have some Vm here, sorry one second. U1 to Un at the most non-zero, then you will have to find Un plus 1 to all the way to Um, these non-zero vectors in null space of A transpose. You can still do, you can still work it out, you will not get any difference in result, only thing you will have to work little more here. It is always good to work with a smaller size, because rank is always less than or equal to minimum of m comma n. So, it is always good to work with smaller size to begin with. Later we will do principal component analysis, which is also an application of data compression using linear algebra, which is almost identical to the SVD analysis. And in fact, SVD is more commonly used as A matrix is more common. Non-square matrices are more common, and you will see that when we do PCA, the first 3 steps are almost identical to what we do for SVD. Okay? So, we will cut back to that here. So, we have so far seen a algebraic approach to SVD, which also looked at the generalized inverse, which we also saw gave us a least square inverse. Now, we saw the entire geometric approach, and it is very constructive. So, unlike the algebraic approach which says yes or no, and this actually makes you do step by step, find the missing portion depending on the rank conditions, and work out a solution purely through geometry and a decomposition. So, it is eventually a matrix decomposition of the type A is broken up into 3 parts, U, sigma, V transpose. So, matrix decomposition is a very common occurrence or a common need, because matrix data as a matrix is very common now, and most data is in very unstructured, sparse, complex, whatever you call that. We really want a equivalent, A equivalent to sigma, which is all the information of A is captured in sigma, but sigma is a diagonal form. Okay. So, this is more or less why SVD has become so ubiquitous and almost indispensable in applications of modern linear algebra, where you get data representation in a matrix form. Thank you very much.